So now let's talk about tensional force. Tension is a force that is exerted by a taut rope on whatever holds its end. F is a vector. This implies that tension has also to be a vector, and tension's direction is always along the cord and away from the object. Now this is very important to recognize that the tensional force is always going to be away from the object that you are looking at. The magnitude of the tension depends on the situation. So if you were to take this idea of these two people holding on to a rope and pulling on the rope, then the tensional force will be equal in magnitude but applied by two different objects, and their directions will be opposite to one another. Similarly, if you were to take mass m and mass m2 and you were to hang them across a pulley, which is considered to be frictionless pulley, then the tensional forces between them will point in the directions shown by the arrow. Note that tension 1 will equal tension 2 in magnitude, but their directions are going to be away from the masses that you are looking at. Tension. This is the force transmitted through a rope from one end to another. So when we are considering these problems, the assumption is that the ideal cord has zero mass, does not stretch, and the tension is same throughout the cord. If you are to look at it carefully, this assumption may or may not hold in all situations. However, this does hold in situations that we will talk about. If the mass is too big, the rope can almost be called as ideal. So assumptions that you will use in order to solve problems like this will be: string is very, very thin. It is almost approaching an ideal condition. And tension is always along the direction of the string. The string has negligible mass with respect to the crate and the person, because the mass of the crate and the mass of the person are too big. Okay? Force P is what is applied to the crate or on the crate by the person. This work is exerted by the worker on the crate, but it is not directly applied to the crate, but in fact it is applied via the string. This force, again, is going to be called tension. So basically the idea is tension is a pulling force. You cannot push with this force. Now, what happens if you have two masses, m1 and m2, and a person is trying to pull them? Again, note what is going to happen. The person is pulling with the force P. He now has to apply more force. For mass m1 and m2, there are two forces acting on m1. A tensional force due to this person pulling, and a resulting tension 2 force, which is opposite to this one, applied because of the presence of m2. Now on M2, there is only one force, which is the resultant force of T2. Even though that these both will be pulled together and their acceleration will be the same, but the forces that are acting on them are different. For the mass 1, there are two forces acting on it directly, one from the person and one from the mass behind it. For the mass 2, there is only one force that's acting on it, and that is tension 2. Now let's look at this concept question. What do you think the answer to this question will be? What will the scale read in this case? 0 newtons, 10 newtons, 20 newtons, or none of the above? The scale in this case will read 10 newtons. Why? The reason why it will read 10 newtons is because the only force that's acting on it is its weight. For a 1 kilogram mass, if you were to calculate the weight, it is going to be mg, and the mg is actually equals to 10 newtons because the value of g is 9.8. So now let's look at another problem. The scale in this case, now we have two masses across a string across two pulleys hanging down together. The scale in this case will read 0 newtons, 100 newtons, 200 newtons, or none of the above. So take a second to think about it. There are two scales, one attached here and one attached here. What will the scale read? Well, in my opinion, it will read 100 newtons. And this is, note very carefully which mass is actually being applied to it. Only this one, because that's the only one that's going towards pulling on the spring. This one is only hanging. So equivalently, what you could have done is just put like a string through here and attached it to a wall. It would still read 100 newtons. So there is no difference between this concept in this question and this question. Only difference is the fact that one is attached to a roof and the other one is attached to another mast. Now here's another really good example. A pulley is hung from a ceiling by a rope. A block of mass M is suspended by another rope that passes over the pulley, and it is attached to the wall. The rope fastened to the wall makes a right angle with the wall. Neglect the masses of the rope and the pulley. Find the tension in the rope from which the pulley hangs and the angle theta. So we are looking for the tension in the rope and the angle theta. So now let's go and do this problem. So let's redraw this picture. I have something like this, hanging, and then there is a mass hanging from the rope. That mass is M, and this angle is theta, and here's my pulley, and this is making an angle 90 degrees. Okay, what is the one thing that I can absolutely say about this problem? One thing I can absolutely say about this problem is that this mass is going to be attracted towards the earth, the center of the earth, by the force of gravity, and that will be given by mg. Okay. The other thing that I can absolutely say for certain is that there is going to be a tensional force that is acting away from the mass, and it's going to be in the upward direction opposite to the force of gravity. So for this mass, I can write for mass the equations of motion. So now how many equations of motion do I'm going to need? Always two, right? Sigma fx and sigma fy. Now let's choose our coordinate system, right? So let's say I choose this one to be my coordinate system, x and y. So that means all the direct forces directed in this direction will be along the x-axis, and all of them directed this way will be along the y-axis. So for my sigma fx, for my mass, is there anything that's here that's directed towards the y-axis? And the answer is no. So I can sort of ignore that, okay? But for my sigma fy, I actually have a value, which is going to be tension pointing upwards and mg that is pointing downwards, because my chosen coordinates, all the forces that go this way, are going to be minus y, okay? Now, is this mass going anywhere? The answer is no, it's not going anywhere, so this equals 0. This implies tension equals mg. Okay, now let's look for the case of the pulley. So this is my pulley. What are the forces that are acting on it? Well, one, there is a force that's acting away from it. That's going to be my force that's keeping this pulley up, right? Let's call that force F. Okay, so this is the force that's keeping it up. Now, another force that's on its pulley is going to be the tension away from it this way, and the tension away from it this way, okay? So if I was to write the equations for the pulley, I can write sigma fx and sigma fy. Now, what is going to be all the forces along the x-axis? Well, I know I have this in my x-axis, which is going to be minus T1, and I have this, which is going to be minus T2, pointing downwards. Now, what about force? Is force in any of those directions? And the answer is no, force is not in any of those directions. So now I have to find the components of the force in these both directions, okay? So I use the head to tail rule in order to figure out what the directions will be for my force. Okay? This means this is going to be F cosine theta, and this is going to be F sine theta, right? Now, which direction will this point? This is pointing towards the plus x-axis, so I can write plus F cosine theta. And this is pointing towards the plus y-axis, so I can write plus F sine theta. Now, since there's no movement of the pulley, I can rewrite these as 0. That means my first equation, let me call this 1 and let me call this 2. For my first equation, T1 equals F cosine theta. And from my equation 2, T2 equals F sine theta. Okay? So now that I know both of these, I also know that these tension 1 have to be equals to tension 2. This is a guaranteed. If there is a rope and both of them are pulling in the same way, they're going to be pulling equally. So I can get rid of my subscripts T1 and T2. Okay? Now, there's multiple ways of doing this. So since you now have equations 1 and equations 2, there are many ways of doing this. One would be to just take T1, plug this value into here. I've actually come up with a very simple solution. I'm going to just divide these two equations with one another. So these tensions will go away, and these forces will go away, right? So what do I get? I get 1 equals cosine theta over sine theta, okay? Sine theta over cosine theta is tangent of theta. So this implies that I can rewrite this as sine theta over cosine theta equals 1, which means tangent theta equals 1, which means theta equals tangent inverse of 1. And tangent inverse of 1, do a really quick calculations, come up with an answer. You have your calculators ready. Tangent inverse of 1 is? Absolutely. So theta is actually equals to 45 degrees. So this theta we just found equals 45 degrees. Okay? Now, since I have a tangent value of tangent theta, I can plug it into pretty much any of these two equations. So let's say I want to plug it into equation 1. T equals F cosine theta, which implies F cosine of 45 degrees, right? And I know from this equation, T equals mg, and that will help me solve for F. As soon as I have the value of M, I can plug it into here and solve for F.